This is Edexcel Further Pure 1, Calculus, Further Methods in Calculus, the Weierstrass or Weierstrass substitution for integration. To be able to follow this, you're going to need to understand the t formulae. Without that, you're not going to be able to follow this video. The Weierstrass substitution is transforming from the variable x to the variable t using the substitution t equals tan x over 2. So if we're transforming for integration, we need to work out a value for dx so that we can substitute a value of dt and some other function of t in to replace dx. So to get dx, we end up differentiating t with respect to x. So tan x is a half sec squared x over 2. And then if we look over at our triangle over here, we can see that sec is going to be hypotenuse over adjacent. And then we square that, so we get 1 plus t squared as the replacement for sec squared x over 2. And of course, we've got to carry the half through. So we can then see that we've got, inverting that, dx over dt equals 2 over 1 plus t squared. So we can then go ahead and substitute t for tan x over 2, and we can end up substituting dx with 2 over 1 plus t squared dt. And of course, using the t formula, we can replace all the other trigonometric functions as well. So if t equals tan x over 2 and dx equals 2 over 1 plus t squared dt, we need to know the substitutions for all the other trig formulae as well. And here they are. So sine x can be changed to 2t over 1 plus t squared and on. And if you need the reciprocal functions, then you just swap numerator and denominator about. So cosec x would be 1 plus t squared all over 2t, and vice versa for sec and cotan. And if you're making a definite integral substitution, then you've got to transform the limits as well using your t equals tan x over 2. In this example, I'm asked to transform cosec x dx into an integral in terms of t using the substitution t equal to tan x over 2. So using my t formulae, I can state that cosec x is going to be equal to 1 plus t squared over 2t when t equals tan x over 2, and dx is going to be equal to 2 over 1 plus t squared dt. So I can substitute those directly in and have my integral, and it will be 1 plus t squared over 2t for cosec x, and I'll replace dx with 2 over 1 plus t squared dt. I can see straight away that I can cancel out the 1 plus t squared terms and 2. So this is going to lead to the integral of 1 over t dt. And if I evaluate that, that is going to be ln t plus the constant of integration. Now, I need to reverse that transformation because it's an indefinite integral. T is equal to tan x over 2, so it's the ln of tan x over 2 plus a constant. And here's that written out more neatly if you need to pause and follow through. So here's a more complicated example. So we've got to first off show that we can do that transformation by using the substitution t equals tan x over 2, and then we have to evaluate a definite integral. And we're given a good hint as to what the form of the answer should be, and we just have to find the value k. So let's go ahead and see if we can do the first part. We'll use the t equals tan x over 2 in our substitution, and from the t formula we've got the expressions for sine x, cos x, and we've already looked at what we would replace dx with. So looking at our integral, we'll end up replacing sine x with 2t over 1 plus t squared, cos x with 1 minus t squared over 1 plus t squared, and dx becomes 2 over 1 plus t squared dt. Now when we look at the denominator of this substitution, you should be able to see that the 1 plus t squareds cancel out. And then if we multiply out that we have on this denominator, we have 3 times 2t, that's 6t. We have minus 4 times 1 and minus 4 times minus t squared, so that's minus 4t squared, but it's a negative times a negative. And because we've got a 2 on the top there, we can halve all of those coefficients, so there we have our final version. So that's the first bit done. So that's the first part of the question done. Now what we've got is a definite integral here. So to be able to work with a transformation of the integral, we need to change the limits as well. So we know that our substitution is t equal to tan x over 2. So the lower part of the integral is when x equals pi over 2. So t equals tan of pi over 4, and that's just 1. So we get 1 as our lower limit of the integral. And then when x equals 2 pi over 3, that'll give us the tan of pi over 3, which is root 3, and that'll give us the upper limit of our integral. So now we have everything in terms of t. We can actually work out the value of our definite integral just using the version in terms of t. My denominator factorizes into those two terms. So I can then split that up into two separate fractions, and I need to work out the values of a and b. And this is an ideal application for the cover-up rule. If you haven't used the cover-up rule yet, it's worth researching that to find out how that works out. The cover-up rule will give us 2/5 for a and negative 1/5 for b. I can then go ahead and integrate those. I'll move the 2 from the 2/5 back onto the numerator of 2t minus 1, and that will then integrate, because it's f dashed of x over f of x, to the natural log of 2t minus 1. The 1 over t plus 2 will integrate to the natural log of t plus 2, and we've got a negative here. We've got a common factor of 1/5, so there's my 1/5. We're using the negative there, so we're dividing by t plus 2, and then I need to apply my two limits. So here's that expression with root 3 substituted in, and here's that expression with 1 substituted in with a negative. I've got a negative ln of 1/3 here, so that's the same as adding the natural log of 3. I've taken a common factor of 1/5 out, and to rationalize the denominator, I'm multiplying top and bottom by root 3 minus 2. So multiplying out those terms, we end up getting negative 1 on the denominator and 8 minus 5 root 3 on the numerator, and bringing in the ln 3 inside the same natural log, we're multiplying by 3. And as we multiply that through, we end up getting 15 root 3 minus 24, which was the form of the answer that we wanted, and this was going to be a 1 over k, so we've completed that with k equaling 5. That was Edexcel Further Pure 1, Calculus Further Methods in Calculus, the Weierstrass substitution for integration. And that concludes this section on further methods in calculus.